Okay, so this is a video on zksnarks, and so this is a pretty recent development in cryptography, and it's used quite extensively by cryptocurrencies, some cryptocurrencies these days. It's not very common. It's still in in development, so a lot of things happening, but it shows a lot of promise, and we have some applications right now, but unfortunately not too much information for people who are not dedicated to the research and to the cryptography world. So I'm going to try to fill that void by giving you some introduction to mid-level understanding of what zksnarks are and how they work in practice. So let's get started with the first point here, which is what they are. So zksnark, the name stands for zk, zero knowledge, s, succinct. There's a non-interactive part, but it's not part of the name. And AR is argument, and finally the K is knowledge. So each of these elements are quite important. So let's start with knowledge. So the stuff that you want to show, the purpose of the zksnark is to show that you know something. You have a piece of information. We talk about what kind of information that we're talking about here, but generally speaking, you know something, and that you want to prove that you have that knowledge. So K is just that part. So the obvious way to show that you know it is to show this information, but in this particular case, we don't want to show this information. We want to prove that we know it without giving any information of that particular piece of knowledge to the person that receives it. So zk, the zero knowledge, is obviously not for you because you have this knowledge, but it's about the person who receives that proof. So you want to prove that you have the knowledge, but whoever receives the proof should not know anything about that piece of information. So zk and k goes together. K is your side, prover, and zk is the verifier. Then you have argument. So it's not knowledge, but it's more like argument of knowledge. And the part here is that you're gonna say that you have this knowledge, but it's not with 100% probability. It's not sure that you have this knowledge. So you have an argument. You can make a pretty good case that you have it, and this pretty good case is actually like 99.99999% sure that you have it. So the probability that whatever you have, the proof that you provided is false. So it's a false positive. It means that it looks like you have it, but in fact you do not have it. That probability of false positive is extremely small, so small that it essentially is irrelevant. Then you have this non-interactive. So typically before these zero knowledge proofs, ZKPs, required some interaction between the prover and the verifier. So the prover will say that he knows something, and the verifier would challenge him. And if the prover can reply to the challenge successfully, it will increase the probability that he has his knowledge. So the verifier will keep challenging, making that probability go higher and higher, until it reaches a point where the verifier feels confident that the prover actually has his knowledge. But this series of challenges and responses are interactive. The verifier has to talk to the prover and keep exchanging this series of messages of challenges and responses. So this is not possible to do if you have a scenario where these proofs are recorded in the blockchain. You would have, in this scenario, you have only the prover would have to record something that will be verified afterwards by many verifiers. Therefore, you cannot have any conversation. So it's very important that this ZKP, zero knowledge proof, is non-interactive for cryptocurrencies and blockchain scenarios. And finally, the S, the succinct, is more of a practical property. In the past, these ZKPs tend to be extremely large, several kilobytes or several megabytes of data. Therefore, it would not be practical to use them in the blockchain, because the blockchain would have to record all these proofs, and the blockchain would be extremely large, and everybody would have to download such a big chunks of data. So that is not acceptable. So all this stuff together means that for these ZKPs to be usable in cryptocurrencies and in blockchains, you need to have all these properties. You have succinct for having a small size, non-interactive because the scenario is essentially offline. You don't have parties talking afterwards. And ZK and K is obviously something that you need to know, otherwise it's pretty pointless. So what is the problem statement that these ZKPs are going to be used for? Usually, the problem statement is showing that you know something that matches a particular condition. So let's give an example. So when you log into a website, when you want to give you give your credentials because you want to authenticate into a website. Yeah, the website wants to check that your credentials, your password, matches whatever it has recorded at the time of registration. So when you register, you gave a username, you gave a password, and this information is recorded. So afterwards, when you log in, you give your username and you give a password, which should match the password that was registered. So the one way for the website to ensure that is to store the username and the password in some database, and compare the password that you give at the moment of login to the password that was stored in the database. But in fact, if the website does this, this is not a good solution, because it means that the database would contain all the username and passwords in plain text, so not encrypted in a form that can be read, because you want to. They would compare that password with the one that you give, and it means that if the website is hacked or the database is stolen, a hacker would have access to all these passwords. So not only he will have access to that website, obviously, but a lot of people reuse their passwords. So if he has, if the user makes the mistake of using the same password on a different website, then the hacker can try using the password that he has stolen and see if it works out. Even if it doesn't work out for all of them, it will probably work for quite a good number of them. So instead, in order to avoid this issue, the standard now is to not store the password in clear form, but store them in a hashed form. So a hash of something is a value that is derived from that password, from that something. So in that case, if you do a hash of a password, you derive some value out of the password in a way that is deterministic, meaning that if you have the password and you apply that hash function, you will always get the same value if you have the same input. So if password hashes to something, then if the same password will hash with the same thing. And it's also made in a way that if you have the hash, you cannot find the password. So it's going one way. from password to hash is easy, but from hash to password is incredibly hard. So if you have this property, what you can do, what the website can do, is to hash the password at the time of registration. So when you register, you enter the password that you want to have. The password is immediately hashed by the website, and the website will store that hash in place of, instead of storing the password, the clear password. Then when you when the user logs in or tries to log in, the password that he gives will be hashed as well, and the hash value will be compared. If they match, then it means that the user has given the proper password. So for this to work, another property that the hash should have is that if two values are different, two passwords are different, they should hash to different values. But that's some of the properties are very classic when it comes to hash for cryptography. So if you choose one of the hash functions that are used in cryptography, then you will have a good solution for that. So that being said, the whole point here is that the problem that the website has is he has to they have to hash the password that is given by the user, and they have to check that result is equal to the value that is stored in the database, because they store hash values and not the original values. The problem for the user, though, is that in order to make this verification, he has to provide his password. So the password will go to the website the moment of login, and the website will do this hashing and this comparison. So you have, if you are the user, you have to give your password, and that's not too bad, because that's what is being done today, right? It's not a solution that is particular super bad, but ideally it would be even better if you didn't have to show your password. So instead, here you would say, I know the password, and I know a password that such that if you hash this password, you will get a value that matches your stored value, and I can prove that to you without giving you my password. So this is kind of like the holy grail, right? So in that case, the problem statement is always is going to be a function. So in that case, it's a function of one parameter, which is the attempted password, and that would be your secret, the value that you don't want to show. So they call it witness sometimes. They call it or solution or secret. And there's some parameter, which is in that case the target value for the hash. So the function would be hash my input, my attempted password, and verify that the result is equal to the target hash. So that's the function, and if that statement is true, then you have a real solution. You know the password. So again, it doesn't mean that you know another password. There could be many different passwords that would hash the same value. It just means that you know one solution. And again, the person who receives that proof, who wants to check that you have that solution, is not interested in knowing the solution. He just wants to know that you have one solution. So what you're gonna send is a proof that you have the solution, or a solution. And what the website would do is that it would verify that the proof that you have means that you have the solution. In other words, is that you would not be able to make that proof unless you have a matching solution to that particular problem. So the tools to come up with that proof are fairly complex. And we are going to talk about all these things in order to understand how in practice this is done first. So first thing is integer fields. So everything that is done in this zksnark will be done with numbers. And even though we were talking about passwords with like text or other problems, we have other like floating numbers and everything. Everything can be converted to a series of bits, and all the math will be done actually in integers for two reasons. One reason is that when you do math with integers, the math is precise. You don't have any rounding issues. If you make sure that you're using just round numbers, and so if you do 1 plus 2 is 3, it's going to be like 2.5, right? And actually we're talking about integer fields, which means that these are integers that are captured in range. So it's not you can't work with whole integers, because the range is infinite. So you have to restrict yourself to a particular range. And these integer fields is basically integers that are between 0 and a certain number n. N is fairly large, right? And if it goes beyond n, then it wraps around to the beginning. An example is if you're talking about time and seconds. If you have 60 seconds, then you wrap to 1 minute, and the seconds will go back to 0. So if you have, for example, 45 seconds, and then you add 20 seconds, you could say that it's 65 seconds, or you can say it's 1 minute with 5 seconds. So it wraps around at 60, and then it goes back to 0. So in that case, it would be just 5 seconds. So these integer fields are basically math that is done in such a set of numbers, but with a much larger range. And the other thing here also is that because it's very large, so the range is actually 2 to the power around 2 to the power 256. The number of possible values that you have in this range is so large that if you are good at choosing a number at random, there will be no chance for having another person choosing exactly the same number as you. So most of these proofs are going to be around this stuff. It's like if you manage to show that you have certain numbers that meet these properties, the verifier will make sure that we check that these properties stand. And if they stand, then the only way for you to have produced that proof is by choosing following the proper rules. You're not going to be able to choose to get these numbers by accident. And again, that's back to this argument of knowledge, the argument, because it's not like these numbers are unique. You can have different numbers also matches the proper set of properties, and they will verify properly. But finding a proper set is so difficult that your probability of doing so without going through the process that we are going to describe here is nearly impossible. So that's around the fact that we're using integer fields that are extremely large. The next topic is elliptic curve cryptography, and this is quite common now in all these quite of these cryptocurrencies, because there's a lot of good properties that you can have in this if you choose the curve appropriately. And these mathematical properties will be very useful for us to derive these proofs and to verify that these proofs are correct. So that's going to be one crucial part of the tool set. And then we have these 4 different things, right? So the first thing that here is arithmetic circuit. So the idea here, and of course this stuff, this is just an overview of the rest. But the idea here is that when you have the problem statement would be which we said it was a function. So a function would be evaluated by in different steps. So if you're talking about a hash, the calculating a hash of something is essentially taking pieces of that password and then combining them, splitting. It's like shuffling cards, but with some fusing, some merging involved, right? Because regardless of the size of the password, the size of the hash is always going to be the same. So there's some shuffling and some mixing, and all these operations are deterministic. So you have to for a given hash, you have to follow the recipe. You have to follow the steps and each of these steps would be since it's executable by a computer, and the computer only understands really like arithmetic operation, plus multiply, plus things like that. At the end, this any calculation, so any problem statement that you want to use, could be turned into a circuit of operations. So we're going to talk more about why it's called arithmetic circuits, but from a very high level, this is a sequence of arithmetic operations which are very basic, basically plus and multiply only, and the first step would be to convert your rather complex, arbitrary complex problem statement into arithmetic circuits, which is kind of not the same as what a CPU does, because at the end of the day, what you have in a CPU is a set of transistors which implements logical gates. So here we're converting a program into a series of arithmetic gates. So then the next step, once you have this circuit, is to turn that into a set of equations. So the idea, right, is that you have originally you have a program because of this problem statement is essentially a program, right? You calculate the hash by executing a series of steps, and then at the end you have a return value, which is going to be either true or false, because either the hash that you have calculated matches the target hash or it doesn't, so true or false. We're going to turn that into a set of equations. Then this set of equations, so it's going to be the form, some very particular form. Knowing the solution would mean the same as knowing a solution to this set of equations. It sounds a little bit like convoluted. Obviously, it is convoluted, but we make sense once we get why we're doing this, right? Because once you have this, once you have turned knowing a solution to the program into knowing a solution to the equation, now you have basically done half the work. Because what you want to do is that you want to show that you know the solution to this equation without giving that solution. So these two problems are basically equivalent. Knowing a solution to the problem statement is the same as knowing a solution to that set of equations. So then you want to prove that you have that solution to these equations, and to do this, we're going to use something called polynomial evaluation, a blind polynomial evaluation. So again, here the idea is that if you have the solution will have a particular form, right? And then you can evaluate that solution and give it to the verifier. And it has to be blind because in that case, blind means the solution that you give has been transformed in a way that the property of being the property remains the same, that the value is scrambled enough that the receiver cannot know the solution itself. Okay, so this whole thing here is again very high overview, and it may seem you may not understand it right now, but that's normal, I would say. It's really complicated, honestly. But we're gonna get into examples and go through these steps in detail. And finally, there's verification. Obviously, this whole thing would have to be verified by whoever receives the proof. Otherwise, this is whole pointless. Then next step is what you do when to set this whole thing up. Right? So we were talking about the tools. Now on practice, what does it mean? So you have this problem, right? So we have this problem, which is like the hash, right? And for each of these problem, you will calculate you will calculate a bunch of transformations, and these transformations will give you some parameters that are very specific to this problem. So each problem would have different parameters. For example, the parameters will be the actual set of equations that your solution must fulfill. Right. Then the part though is that to prove that you have the solution, it's not practical. It's not going to be succinct. So in order to have the succinct property, we have to make a compromise in a way, and choose to evaluate to choose randomly only one point. So instead of saying that you have a proof that works everywhere, we are going to say that you have a proof that works only at one point. And the trick here is that if you choose that point at random and nobody knows where that point is, then it's basically same guarantee. This is like taking a test. So imagine that you take a test on the topic that is fairly large, right? You could receive 100,000 of questions, and then prove that you have an in-depth understanding of that subject. But here the test will only give one question. So if you know the question in advance, obviously regardless of the difficulty of the question, you could prepare yourself in advance and then you know the answer. Right? But if that question is so random that there's no way for you to know it, then if you are able to answer that question and no luck would be involved because it's really random, then it means that you were good everywhere. So that's kind of like the idea. And to prepare for this, there's this setup phase. So it's very important that during this setup phase, nobody knows what question will be asked later. So this is one of the main issues regarding the current implementation of zksnarks. There's this called toxic waste, because there's a value that is very important in the system, in the zksnark generation and the workflow. But it's also equally important that nobody knows that value. Then what you do is you have an algorithm that takes the setup parameters. They also take the public parameter. So in that case, it would be an example. It would be the target hash, and it takes your secret. It takes the password. So you mix all this stuff. You have this algorithm that evaluates all these things, and then it creates a proof. And that proof, if it's a good proof, should be fairly small, right? But it's not like tiny. It's still a few hundred bytes, for example. So that's not too bad, right? It's rather small. And it's small, but it's not so small that you can find this proof randomly. If you have 200 bytes, and then the chances for you to to pick randomly a valid sequence of 200 bytes is completely negligible. So of course, this proof has to meet a particular relation that is also again specific to that particular problem statement, and the verifier can check that yes, indeed, the proof that you are given matches this requirement, this particular relationship, and this relationship is again specific to that particular problem. And since it does, and if it fits these properties, then it shows that you have a solution. And other things, of course, is that the proof should not give you shouldn't give the receiver, the verifier, any knowledge of the solution that was used to produce it. So that's the workflow, right? And it's like a little bit of magic, right? Because why would you imagine that? Again, if we go back to the problem, like how can you prove that you have something without actually showing that something? In very, very high level is you can prove that you have it because you can find a solution that is derived from like you can find something that is derived from that solution, that it would be extremely hard to do without actually going through the steps of the proof generation while taking the proper input, the proper witness, the proper solution. And that's only possible because there's a lot of stuff that we're going to talk about in the proof generation and verification, but also it's also because the proof is large enough that randomly it is not possible to be so lucky. So how do we do the setup? So the setup is derived from the problem statement, right? So if you have something about calculating hash, obviously you're gonna have different parameters than if you have a problem about solving a set of equations. But the good thing is that regardless of the problem, it should be convertible into this arithmetic circuit. Because every statement that can be computed by a computer, but be evaluated by a computer, is eventually going to be a set of atomic operations such as multiplication and additions. So this conversion is to arithmetic circuit and quadratic program is done. Offline is done once and for all for a given problem. So this would take quite a lot of time, but it's not intractable. It's actually linear in the time taken to do this is about linear in the complexity of the problem. And then another output of this would be this common reference string. So this is the toxic stuff that we talked about. So basically, due to the fact that we don't want to evaluate to verify the proof everywhere, but we want to verify the proof at a certain point. So we need to agree. So both producer of the proof and verifier, so prover and verifier, needs to agree on that common reference. So some data that we have to share, but the generation of that reference should be forgotten, and the reason why would be much clearer once we get into the details of how this string is generated and what's the purpose. So that's the setup, and it has to be done once and for all. Then the process of generation and verification goes through the problem was turned into a polynomial problem. So we're gonna have this evaluation. Then we're gonna have to show that you have a solution for A, B, C, H. So these values will be we'll come back to this later. And then you have to prove that these numbers that you give they were calculated properly. So there are two things. You have to make sure, you have to prove that these numbers were calculated properly, and you have to prove to show that these numbers, they fit a particular relationship. And that's the job of the prover, and the job of the verifier is to make sure that whatever we just said before stands true. So he has to make some checks. So actually, in short, the proof would be a series of points in some space, and these points will have some relationship. So you then verify that they were constructed in a particular way, so that they have some precise relationship that the verifier can check, and finding these points means that you have a solution to this particular problem. So this is really very high level, and now we kind of go back and talk about this part here, and go through these steps. So taking the example of the hash function is way too complicated, because the hash function has many steps, and at the end we will have a set of equations, which will be like thousands of equations and thousands of parameters. So that's not going to be possible to do as an example. So the example that I've taken is actually taken straight from blog, from the guy who created for Ethereum, and also from the guys who created Zcash. So don't take credit for any of these, the content of this presentation. I just want to be sure that it's clear that all this data is I've got it from the internet, and I always encourage you to read more about this.